That's phew, okay. When we talk about rational functions, because that's what we're moving into, what does that even mean? Do you think any places that you've seen the word rational used before? No? Okay. Well, the root is ratio. And a ratio is a way of comparing two things, right? And one way of expressing a ratio is with a fraction. So when we see rational, we're going to think fraction. Rational numbers are anything that you can write as a fraction. Anything that can be written as technically an integer fraction. Like you can't have a thing that looks like a fraction but has, a square root in it or pi or something. A fraction of two integers, right? Or a ratio between two integers. So for example, things like 1/2 or -3/4 that, look like fractions, but also stuff like, also stuff like 2 or 0 or 0.1 or, whatever. These are all things that can be written as a fraction, whether they're currently expressed as a fraction or not, right? So like 2, I could write as 2/1, or 4/2, or a million other ways. 0, I could write as 0 over anything. 0.1 is the same as 1/10, right? Some examples of things that are not rational would be like the square root of 2, or any kind of like root that doesn't, generally any kind of root that doesn't simplify in a nice way. Pi would be another one, because there's no way to write it as a fraction of integers. Okay, so what rational numbers are is taking the integers, which are the nice-ish numbers, right? The things that you can, count with your fingers, positive or negative, and dividing one by another, and making a fraction out of it. What rational functions are, right on time with the leaf blowers this morning. I love it. Sounds like a lawnmower or something out there too. Good. Rational, what am I talking about? Rational functions are fractions, but they're fractions that we make up out of polynomials, right? So we've just spent 3 weeks talking about polynomials. Polynomials are these nice, well-behaved functions that are defined everywhere and have all these like cool properties, like they're always continuous and they're pretty easy to work with as things go. So rational functions are what happens when we take a polynomial divided by another one. So for example, I don't know, I'm just going to write some stuff down, like the specifics aren't really important. Minus 3 over x squared plus 5x plus 2, whatever, that kind of stuff. One polynomial divided by another. So that's what we're going to be looking at for the next week. Like I said, today and tomorrow, basically, we're going to look at how they behave as functions and talk about graphs and domain and range and anything interesting that happens, that kind of stuff. Thursday and Friday, we'll focus more in on, okay, well, what about like solving equations involving these, or how do we use them in applications, that kind of stuff. First, though, we need to kind of start with, because we're looking at a new kind of thing, so we sort of need a way to get into it in the first place, right? Like a simple-ish example that we can use as kind of how I've been counting things now. I don't know, just stuff for everybody. An example of something that we can look at that's going to kind of tell us what's going on and give us sort of a, like a prototype repair function. Like that. So let's take, 5-10 minutes. There's a QR code there that'll pull up a graph of y equals 1 over x. That's kind of about as simple a thing as we can have that's, different than things that we already know, right? It's not a polynomial. It is a genuine rational function. Where some interesting things are going to happen that's, different than other stuff we look at, but kind of about as simple as we can make it. So y'all go ahead and move around, get into the groups, look at that graph and try to come up with, domain, range, x and y intercepts. Basically, like, what do you notice about the function? Is there anything that any questions that brings up? That kind of thing. Okay, so what do you see? What? Go now? Okay. What's, I don't know, different, weird about this compared to, think about all the stuff we've been looking at lately, right? quadratics, well, you just get a parabola, right? So this U-shaped thing that, you know, is defined everywhere, nice and smooth, no like weird stuff, no sharp corners, no jumps, no breaks, whatever. And polynomials. Polynomials are, you know, a little bit like a big, like old-fashioned, like wooden roller coaster track, right? Kind of gradual, like ups and downs and stuff, and then the ends go off somewhere. But again, like continuous, defined everywhere, no, you know, real harsh, sudden stuff, that kind of thing. What's different about this? It splits, right? Mary, what do you mean it splits? Or how about, does everybody agree with what Mary said, that it splits in a sense? Yeah, I mean, think about reading it left to right. If you're going to describe this to somebody, kind of here, right, it starts sort of turning down, but then to get to the next piece, you got to kind of jump, right? Okay. So it splits in a sense. There's kind of two like branches to the thing, right? We haven't really seen anything where that happens before. We call that a discontinuity, where it splits like that, where it breaks into another piece. We haven't really dealt with anything up to this point that's not continuous everywhere. So there's that. Now looking at the like individual branches, right? Like just focus in on this part, right? On the left-hand side of the graph. Everything looks, you know, fine. Like that part on its own doesn't really look all that, you know, scary or intimidating or weird. If you were going to describe that to somebody, how would you do that? You start with the sign, right? Or the y value is positive or negative. Well, negative, right? It lives underneath the x-axis. Okay, so they're all negative. Here they're kind of really close to horizontal, right? Like they're pretty close to the x-axis. But then it gets steeper and steeper here, right? Kind of curves in, kind of squeezes into this corner a little bit. But then it gets really steep, right? Until it's kind of almost vertical. I don't know if you like played around with the graph at all, but if you there we go. If you kind of mess around with the graph a little bit, you can see that like if you go out far enough, there's kind of always a little bit of a gap there, right? Okay, and then the other side in quadrant one, it kind of looks like the mirror image of that, right? Yeah, well, there's some stuff to unpack with that mirror image thing that we've seen before, but again, it kind of, you know, has this sort of like L-shape kind of thing, squeezes into that corner a little bit. What do you think happens around the axes, the coordinate axis, the y-axis, the x-axis? What does it look like it's doing? Well, think about that for a minute. I'll talk about it. Look at what's happening near the x-axis, near the y-axis. Play around with the graph, move out, zoom, you know, whatever, that kind of thing. See if you can get a feel for what's going on near those coordinate axes. We're looking at y equals 1 over x, right? Sometimes that's called the reciprocal function because what it does is if you plug a thing in, it gives you its reciprocal, right? If x is 2, then the y value I get from that function would be 1/2, which is the reciprocal of 2, right? So that's what it does. Here it is, same graph, but I've zoomed way out, so we're looking at like, about 2,500 or something in each direction, right? And it just looks like a, big red plus sign, basically, right? Looks a lot like the coordinate axes. And I'm going to zoom in way out here at 2,000. It's going to take me a minute, but okay, there we go. Now, it's a little bit hard to keep track of stuff, but here's the x-axis, here's the function, right? Now we're way out here, and if you look at the scale, like these are in the, we're getting tiny little decimal things here, right? 0.002. But here's the x-axis, here's the function. One of the things I asked you to find were x and y intercepts, right? Which is anywhere it crosses the x-axis or the y-axis. Based on what you see here, what do you think this thing's going to have for x-intercepts? Is it going to cross the x-axis anywhere? Why not? You can't divide it by 0. You can't divide by 0, and you also can't get a reciprocal for 0, right? So I can't let x be 0 because 1 divided by 0 is undefined. But y can't be 0 either, because if you try to solve, write that. 0 equals 1 over x. Well, that doesn't make any sense, right? There's no x value that's going to give you 0 back there. Now you can see here maybe that, like here I am out at x equals 2,000. The reciprocal of that is going to be really small, right? 1 over 2,000, but it's still going to be a positive number. So there's no way to make this work. There's also no way to make this work. So because of that, we're not going to get any x-intercepts, and we're not going to get any y-intercepts either, right? So back to just like a normal default window, the further out you go in any of these four directions, right? Left, right, up, and down. The further out you go, the closer that graph is going to squeeze into the coordinate axes, but without ever like actually reaching it or touching it or crossing it or anything, right? Because of that, because I can't let x be 0, and it's also not going to work if I try to let y be 0. I'm not going to get a solution. This little space here, where you can, sort of like tell a difference, right? Where it's sort of as far away from the axis as it's ever going to get. That's because you're taking the reciprocal of like smallish numbers, right? Numbers that are close to 1. It passes through 1, 1, right? Because 1's reciprocal is itself. So what happens is, further out you go to the left and right, the end behavior, right? That's how we described going out to the left and right. Large x values, positive or negative. The end behavior of this thing is that it just flattens out and levels off toward the x-axis. Now, it's always away from it a little bit if you go out far enough, right? On this side, it's always going to be just above. On this side, it's always going to be just below. But if I'm going to describe the end behavior like we've been doing the last couple of weeks, I would just say like it's level, right? It's level, and where it levels off is the x-axis. So keep that in mind. That's how we're going to kind of talk about end behavior now. And here, as I approach 0 from the left or from the right, as I approach the y-axis, this end, where the x values are negative, these numbers get really, really big, right? That's why it gets really steep and is pointing sort of down. These are positive, so they turn into really big positive numbers, steep but pointing up. So the way we describe all of this stuff, let me do this. The way we describe all this stuff is to say that this has what we call a horizontal asymptote, and I'll, write that in a second, but okay, I can't. This is fun. Hang on. Nothing works. Here we go. Why is nothing? There we go. Okay, great. Sorry. We're back in business. All right, so that's something like this. I don't know what's happening, y'all. Sorry. Okay. Here, because there's this horizontal line that kind of describes what the left-right end behavior does, right? Anytime we have a line like that that sort of shows like big picture what's going on, right? That's the line that the thing follows. If I get away from this stuff in the middle, that's the line that follows. We call that an asymptote. Since I can't write it on the screen. Oh no, this word is awful. Asymptote. This is a horizontal one. So it's got a horizontal asymptote. You describe it as the horizontal line that it is, right? So that would be y equals 0. There's also a vertical line that does the same thing, right? Where is it? X equals 0, the x-axis, right? Again, thinking about it from a vertical kind of perspective, I can imagine a vertical line that I can sort of like squeeze in there that's not really part of the function, but it does kind of frame the function. Does that sort of make sense? Like the function itself doesn't cross x equals 0. 0 is not in the domain because division by 0 is undefined. But if I drew that line in there, and typically I would draw this if I could do such things at the moment with like a dashed line or something, or maybe make it like a different color, so if you got a red pen or something like that. A dashed line, because again, it's not really part of the function, but it does like frame the function, right? So a lot of what we're going to do to graph these things is start by finding those, because those are, we'll get into the details, but those are things that we can do, kind of fairly easily by using all of our polynomial stuff that we've been working on the last few weeks. We can find those, and then we've got kind of a framework for everything, and then we can, find the graph of the actual function. Okay, so with all of that in mind, you should be able to write down what the domain and range are for this thing now. Or if I can actually draw things now. No, okay, great. Okay. Oh my goodness gracious. All right. So domain and range for y equals 1 over x. Everything except, where's the one place this has a problem? 0, right? Domain, we're talking x values. The one x value that would not work here is 0, because you can't divide by 0, right? So everything except 0. How can we write everything except 0? Well, first is everything to the left of 0, which would be negative infinity to 0. Skip over 0, right? So open union with 0 to infinity. Again, there's a vertical asymptote at x equals 0. That's this one. There's also a horizontal. Okay. Okay, now the things are just deleting themselves. Now my finger doesn't even work at y equals 0. Okay, what is happening? Y equals 0, that's that one. Because of those asymptotes, because of the way the thing behaves, because of this discussion about like x can't be 0 but neither can y, it doesn't have any x or y intercepts. What would the range be? Y values? Same thing, right? Negative infinity, this is pointing down, right? Negative infinity up to not quite, but almost 0, right? As close to it as you want. Skip over 0, then 0 up to positive infinity. So the range would be the same. In interval notation would look the same. Okay. Anybody have any questions about anything so far? Okay. So I gave you some graphs of things to look at. These are all similar sorts of things. So just based on what you see in the graph and the asymptotes that I've labeled, I know the copies might be a little bit hard to see, but the scale there is by 2s. That's the code change because there's no reason for it to be, and you can't really read it on the printout. But based on that, so like looking at this one, and again, basically that idea that asymptotes are going to sort of frame the thing in, right? So if I'm marking an asymptote on a graph that I'm giving you, you can assume then that like what's going to happen is that it's going to sort of continue to like squeeze in on that line the further out you go. So based on what you see here then, where are the, well, okay, sorry. Does it have any asymptotes? Yes. Where are they? Sorry, say it again. X equals 2. There's a vertical asymptote. I'm going to start abbreviating that because it's a lot to write. At x equals 2. This is another place where, it is a line. It's an equation of a line. So I'm going to make kind of a big deal about the x equals part of it because that's the way you define a vertical line. There's also a horizontal asymptote. Where? Y equals 0. Okay, so this is the vertical one. This is the horizontal one. Based on that and what we see about the graph, what do we think about the domain and the range? Say that again. They're not going to be the same as the last one, as 1 over x, right? What's the domain? Negative infinity to 2. And then 2 to infinity. And again, just the way you want to like read that or think about that is everything except 2, right? We're just skipping over 2. Okay. What about the range? Mm-hmm. Yep. Everybody agrees, everybody see that? Especially the domain part. The range thing is going to start to get a little bit complicated. We're not going to spend too much more time on that. We'll look at it in these couple of examples, but the range thing gets a little bit harder here. The domain part, though, the idea here, what's going on, is that this vertical asymptote at x equals 2, that's showing us a place where we would end up dividing by 0, right? I don't know what the function looks like for this just yet, but that's a place where division by 0 would happen. That's why when you get close to it, the ends start getting really steep because you're dividing by something really close to 0. If you divide by a really small number, you get a really big number back, right?
So that's why these things get really steep like that and sort of, turn like almost vertical. That's why we get this vertical asymptote here. That's why we get this sort of break in the domain and where it's defined.
Okay, so take a minute, try to do the same thing with the others there, the other three.
All right, so that's the second one, the one in the upper right. What do you see in terms of the asymptotes?
There's a horizontal at y equals 2. There's a vertical at x equals -1.
What about the domain and the range then?
Yep. Mm-hmm. And the range, and based on kind of what we've seen everywhere else,
Everything except for 2, right? Sort of again, like squeezing in on that line without crossing. These are all
the first 3 here.
so those 2 and this one, those are all just shifts of 1 over x, right? So just like using that like a pair function, shifting left, right, up, and down. So they're going to behave the same way. The graphs look, like the same thing, just picked up and placed in a different spot. When you do that, the asymptotes and everything move along with it. Also notice, I meant to point this out, but notice that the one that we started with, 1 over x, it didn't have any intercepts, right? X or y intercepts. Some of these do though, right? So they can still, I don't want you to think like they can never cross the coordinate axis. They can. It's just that they can't in particular places because of the way they are, right? There are going to be certain values that they can't cross, especially those vertical asymptotes. All right, this one, similar sort of deal. Again, same function, just shifted down a couple. So vertical asymptote at x equals 0, horizontal at y equals -2. And range. Okay, so there's all that. Again, like this one's got an x-intercept there, right? But it doesn't cross its own asymptote. What about the last one? This is different, right? This is, again, rational functions, it's a big family of things. They don't all look exactly the same, but it's some kind of polynomial on top divided by some other kind of polynomial on bottom. This one looks like this. So what's different? There's two vertical asymptotes, right? You can have more than one. There's no limit really on how many you could have, just like, you know, with polynomials, you can have as many zeros as you want. It's the same idea. So there's two vertical asymptotes.
They are, looks like -2, x equals -2 and x equals 1. There's a horizontal asymptote of y equals 0.
What else is different here than the others that we've been looking at? There's three like pieces to the graph, right? Instead of just two, you know, chunks, there are three. There's this stuff and this stuff and this stuff. These look similar in shape to what we've seen. This one looks different, right? That middle piece looks almost like a cubic sort of. So that's a little bit different. Let's do one thing at a time though. If there's two vertical asymptotes
And three like pieces to the graph, then what's the domain going to look like? There's going to be like 3 intervals, right? So we're going to have to union a couple of times. They are -infinity to -2 and -2 to 1 and 1 to infinity.
Okay. Now again, I want you to notice like the way that stuff all kind of fits together, right? 3 branches to the graph, 3 intervals to write the domain down, 2 vertical asymptotes, and the vertical asymptotes go here and here, right? Basically, they fill in those gaps where the unions are, right? Where we've got open intervals on both sides and we're unioning around them. That means you're just skipping over a single point. Well, that single point you're skipping over is exactly where that vertical break happens. Okay. Now let's do the same thing for the range. There's one horizontal asymptote of y equals 0, but if we're talking about range, we mean y values. So what is different about that than the others that we've been looking at? It crosses it, right? The others that we looked at, the horizontal asymptote showed us kind of, you know, this line that the thing like squeezes in on, you know, as you go off toward the end behavior. But there's this middle chunk, and this middle chunk, as far as I can tell, goes through that line, right? Like there is an x-intercept there. And unless, you know, somehow I'd like misled you with the graph, but that's why the range thing gets a little bit more complicated. What horizontal asymptotes do is tell you about the end behavior. So that still describes what the ends do, right? That end starts to, you know, going off to the right. That starts to look an awful lot like that horizontal line. This one going off to the left, same thing. It looks a lot like that horizontal line. It doesn't tell you about the stuff in the middle necessarily. So the range here is the range here is all the real numbers, right? So it does actually cross that line. That's why I said a minute ago, we're not going to talk about range as much because it gets more complicated. We'll develop the tools that we need to do that, but for the most part, we're going to kind of leave off the range thing for now. So vertical asymptotes, those tell us about domain in a pretty definitive way. Like you cannot cross a vertical asymptote because vertical asymptotes happen here. They happen at times like this, and you can't divide by 0 like ever. That never works, right? So that's why vertical asymptotes come in. Horizontal ones happen for a different reason, and we'll get into that. But because of what they do, all they really tell us about is the ends, right? Now, again, they kind of like frame things out, but not necessarily everything in the middle. Okay. All right. So let's take a look at another thing and sort of looking at it symbolically. So look at y equals 1 over x minus 2. Graph that real quick. If you have a calculator with you, you might want to graph it there too, just to kind of get a feel for, how that looks a little bit different. Okay, so if you've got your calculator, you grab it that way, like the picture is not quite as nice, right? It's gonna be all pixelated, blocky, you know how it is, because it's a screen from 1987. Desmos is a little bit nicer, but again, like if I don't have that grid there, and no one gave us the the other graphs that we looked at, like I gave you the asymptotes, right? I drew them on there for you, so you can tell exactly where they are. It's a little bit harder to tell here exactly where that happens, right? I can still see that there's a break in the graph, and you want to be, kind of training yourself to, spot this sort of thing. I can still imagine a vertical line in here, but it's hard to tell exactly where it happens. So how do we figure it out? Or, more generally, if we're just trying to do it from the equation, right? If I'm trying to look at this and say like, okay, here's what I know, just kind of at first glance right off the bat, what do I need to look for? The -2, what's the -2 tell you? That it happens, that something happens at +2? Why? What happens if you take this and set it equal to 0? You get x equals 2. Okay, what does that mean working, sort of backwards? If I try to take x equals 2 and plug it into this, what happens? You get 1 over 0, which just like it's always been is bad news, right? That's undefined, that doesn't work. Now what happens then for things that are close to 2, like 2.1, 2.00, as close to 2 as you want? You're not going to get 1 over 0, but you are going to get 1 over a small number, right? Well, that gives you the reciprocal of the small number. The reciprocal of the small number is big number. That's why it does this, turn really steep, get almost vertical asymptote kind of thing. So what I can tell by looking at this is that x equals 2 is going to be a problem. If I let x be 2, I get 1 over 0. If I get 1 over 0, I'm going to have vertical asymptote somewhere. So x equals 2 is where that vertical asymptote occurs. And then, if you look at that, you can tell like, okay, well, that looks right. If I just sort of, tried to eyeball it and said like, well, maybe it's 3. Well, no, it's not 3 because that's not quite the right spot, right? That doesn't squeeze into that, gap between the things the way that it ought to. Okay. So we've got fractions that are made of polynomials. And what we've just seen, or what seems to be happening, is that we're going to be pretty interested in the zeros of the denominator, right? Good thing we know so much about finding zeros of polynomials, right? Get excited, everybody. None of that stuff is gone. We're going to keep using it, right? So, yeah, so we're going to be really interested in finding zeros of the denominator, because those are going to be places where these, breaks in the graph, breaks in the domain, these vertical asymptotes are going to occur. So, for this one, maybe, that has vertical asymptotes there and there. What do you think that means about what the denominator of the function looks like?
x plus 2 and x minus 1.
These places where bad stuff happens, right? Where the function is behaves poorly, right? It gets really unstable near those points. These places where bad things happen come from zeros of the denominator. If there's zeros of the denominator, then we know factors, right? So x equals -2 being a vertical asymptote tells me there's a factor in the denominator that looks like x plus 2. X equals 1 being a vertical asymptote tells me there's a factor that looks like x minus 1. Okay, so we will pick up there tomorrow. Hang on to those. We'll talk some more about this stuff and how it all fits together. And
Y'all have a good day. I'll see you tomorrow.